And welcome to Story Untold. I'm Martin Baumann, and this week I'm going back in the archives to one of the most interesting people I've interviewed. Dr. Adrian Owen is his name. He's a cognitive neuroscientist from the UK. And if you've heard his name before, it's because he's done some pretty cool work. He's most famous for his breakthrough in finding signs of consciousness in patients thought to be in a vegetative state. And he did it by looking at the brain when it's being asked to imagine different things. I spoke with him back in 2014 at Western University. He was a newly minted Canada Excellence Research Chair at the time, and he's still there today. It's a shorter episode, but it's a good one. Here it is.
You know, you've done a lot of really remarkable things over these past few years here in the field of being able to get these patients to communicate who we didn't think would be able to communicate before. But it all started in a way with a game of tennis. Tell me about that breakthrough.
That breakthrough occurred in 2006. And at that point, we had been trying for many years to work out ways of detecting consciousness or any sort of cognitive function in patients who might otherwise appear to be in a vegetative state. And we had tried all sorts of things, from having them listen to speech while their brains were being scanned, to even telling them jokes, but we hadn't really cracked it. We hadn't really found the key to working out whether somebody was conscious. And then we realized that we could ask people to imagine that they were performing a motor act, moving their arms around. And of course, if you imagine playing tennis, that's a very good way of getting people to think about moving their arms around. And in the very first patient that we tried, we asked them to imagine playing tennis, and her brain lit up like a Christmas tree. Each time we asked her to do this, the same thing happened. Her brain would activate in response to being asked to imagine playing tennis, and that was a clear signal for us that she was conscious and aware. She understood the instructions we were giving her, and she knew what we were asking her to do.
So that was 2006. You would have been in Cambridge at the time. How long had the process been before then? How many years had you been working on it until that breakthrough?
So the first patient I saw was in 1997, and this was a completely chance occurrence. It was a patient who came into the intensive care unit in Addenbrooke's Hospital in Cambridge, where I was working. She had lapsed into a state of unconsciousness. She was in a vegetative state, and my colleagues and I just thought it would be a good idea to put her into the brain scanner to try and work out whether there were any signs of residual activity, and that there were. I don't know whether she was conscious or not, but there were certainly parts of her brain that were still responding. And that was the first indication any of us ever had that some of these patients aren't what they appear to be.
What was it that really sparked your interest in this field in the first place?
Well, my training was in brain imaging, and up until 1997 I had been involved in many studies using various types of brain scanners in healthy participants, really to try and work out how the brain works, how different parts of the brain perform different psychological functions. And it was only in 1997 when I met this patient who was presumed to be in a vegetative state, and we decided to scan her, that I realized that it's actually much more interesting to apply these techniques to the solutions of particular clinical problems. I think basic cognitive neuroscience, brain scanning in healthy participants, is an important thing. I could never have got to where I am with the patients had we not had that groundwork. But for me, working with patients and trying to find out which ones are conscious, which ones aren't, who might recover, who is unlikely to recover, it's much more fulfilling.
When you get that reaction from a patient and you realize that they're responding to what you're asking them to do, what are the next questions that you ask them from then on?
Well, actually, it's still very early days. I guess because we've received a lot of attention for this work, I think people think we've been doing this for many years. In fact, we only communicated with the patient for the first time in 2010, and it's still pretty rare. It's a pretty rare occurrence. When it does happen, really the thing we're most interested in doing immediately is finding out if the patient knows where they are, who they are, what has happened to them, because it's very easy to imagine that they might be in a state of complete confusion. They may have no idea who they are, where they are, how long they've been there, and these sorts of things. So we tend to ask very basic questions about who they are, whether they know they're in a hospital rather than another noisy environment like a supermarket, for example. Do they know how long they've been in that situation? And then once we've established a good line of communication, then we'll start to explore more clinically, I think, important questions like what do they like to do? How do they like to be entertained? Do they like to watch TV or listen to the radio? And most importantly, as we did last year in the patient that you've already mentioned, we asked whether he was in any pain, because I think that's an extremely important question, and of course it's something that we can do something about.
It was 2011 then when you came to Western here, or at least when the facility opened up. Tell me about the team that you're working with here, how many people you have working with you here.
I have a fantastic team. I could not possibly speak more highly of them. They're great. Some of them came with me from Cambridge. Essentially, I offered my whole team there the opportunity to move to Western when I received the Canada Excellence Research Chair Award. Most of them came, I'm very glad to say. Others I've taken on since we came here. And we have experts in quite a variety of different types of technologies. I think that's something that often surprises people. We're not all cognitive neuroscientists, at least we're not all the same type of cognitive neuroscientists. So some members of my team work with FMRI, functional magnetic resonance imaging. Others are experts in electroencephalography, or EEG. We've recently taken on an expert in sleep studies, and that's because we're using sleep as a way of mimicking what might happen in some of our patients when they lose consciousness. Typically those are all research scientists or postdocs, but we also have graduate students working in all those different areas in EEG, fMRI, and sleep studies. We even have postdoctoral researcher now working on galvanic skin responses, the sweat response from the hand, in order to try and detect emotional responses in some patients who are presumed to be vegetative. So we have across the team, a very wide variety of expertise.
You mentioned the EEGs very briefly there. Can you tell me a little bit about how they work and how they are different from an fMRI and how that would work?
Well, what you're doing is essentially the same thing. You're measuring brain activity, if you like, and we're particularly interested in finding out whether patients who might appear to be vegetative have patterns of brain activity that look similar to healthy participants when we present them with certain types of stimuli, such as sounds or movies and these sorts of things. The way that you go about acquiring that brain activity is quite different in fMRI and EEG. Essentially, fMRI is looking at is how blood is, or how oxygen is distributed in blood throughout the brain. Areas of the brain that are working hardest will draw more blood. You'll tend to see more oxygen in those areas, and we can detect, therefore, which parts of the brain are activating. EEG, or electroencephalography, works in an entirely different way, which is with a large array of electrodes on the outside of the head. We measure the electrical activity that is being emitted from the brain as the person takes part in various psychological processes. They have pros and cons. fMRI tends to have better, what we refer to as spatial resolution. You can see the difference between different areas in the brain rather better than you can with EEG. You can localize the responses a little bit better. EEG tends to be much faster. You can measure responses in the brain with millisecond accuracy, whereas in fMRI it tends to take at least a few seconds. And as you said, fMRI is rather more expensive, and of course it's not portable, whereas the EEG, we're able to go and visit patients in their homes, in their nursing homes, in hospitals, and test them in their own beds using our EEG Jeep, which is a fully equipped Jeep with all of our EEG equipment that we use to go out on the road and visit patients.
One of the exciting possibilities for the future that this opens up is the possibility of a brain-computer interface of sorts that would allow patients to potentially communicate again with the outside world. How far are we from seeing something like that, or how would that work? Tell me a little bit about that.
So that's obviously, there's an awful lot of interest in a brain-computer interface, and particularly in a brain-computer interface for patients who are unable to respond in any other way. It's actually a really tricky problem, though. Essentially, what you're trying to do is to take the responses from the EEG and turn them into some form of communication. Typically, the sorts of things we would like to try and create would be to have a machine that a person could use to signal a yes or a no by simply changing the pattern of activity in their brain, or even further, perhaps they could spell words. Now, these systems do exist, but they have a number of problems, and I think some people often tend to read about them or see these systems on television and wonder why it is we haven't just applied them in our patients. But they're actually quite tricky to apply in our patient population. One reason is because they often require a lot of practice. You can't just put the headset on and launch your browser and start using the internet with a brain-computer interface. They typically require lots and lots of training, and that's training by you learning to modulate your brain activity, but also training of the algorithms that are used to decode what it is that's coming out of the brain. And that, can be hundreds of hours of practice in some cases. It's hard to imagine doing that in a vegetative state patient or in a patient that's had a very serious brain injury. Getting them to put in hundreds of hours of practice is something that is not very straightforward. Also, these things tend to work much better on healthy brains that are the shape that brains are supposed to be, and that's the way they're designed. And many of our patients don't have healthy brains, or brains that are the shape they were when they were born. Obviously, if they've had a very serious brain injury, particularly a traumatic brain injury, then the brain will not be the shape that the algorithm is expecting to be, that's trying to work out what it is that the person's thinking or trying to respond with. So that's another reason why it's a technical challenge. So I think all of these things will be overcome in time, but it really isn't a trivial technical problem.
I've read a little bit. You've also been doing research with conditions like Parkinson's and Alzheimer's. Tell me about that research and where that's going.
So that's addressing rather different questions, actually. I've worked for much longer in neurodegenerative diseases than I have in brain injury or the vegetative and the coma patients that we've just been discussing. So my PhD back in 1992 was a PhD about Parkinson's disease and its relationship to Alzheimer's disease, and in particular about the types of cognitive deficits that patients with Parkinson's disease develop. So one of the interesting characteristics of Parkinson's disease is not only do these patients develop motor deficits, problems with movement and rigidity that people are very familiar with, patients also have problems with attention and with memory and with concentration and planning. And some of the earliest neuroscience that I was involved with really was mapping these deficits, trying to find out, trying to understand the nature of cognitive deficits in Parkinson's disease, how they relate to the sorts of cognitive deficits that we see in Alzheimer's disease. And of course that's more widely known. I think most people realize that Alzheimer's patients often have memory deficits. It's not so well known in Parkinson's disease. And also whether these types of deficits can be improved in any way. And that work has continued for more than 20 years now. The sorts of issues that we're looking at now are whether we can use types of brain training, cognitive training, to improve performance improve cognitive performance in patients who have Parkinson's disease. So we have a cognitive website. It's called CambridgeBrainSciences.com. It's entirely free. People can log in there and test their own cognitive function, test their planning, their memory, their attention, and we use that to test patients. We send them home and we ask them to log in and test themselves on these cognitive tasks to try and map their cognitive functions.
What do you see as the next step in your research, and what do you see as the implications of the research you're doing right now?
Okay, so one of the real stumbling blocks that we have had, it's been very successful for us, things like getting people to imagine playing tennis, but in a sense it's a stumbling block because we're still requiring the patient to make a response. It's a mental response, but it is a response, and it's quite challenging to ask somebody to lie in a scanner and imagine playing tennis and then stop doing that and then imagine something else. And it's quite likely that many of these patients who have had very serious brain injuries just don't have the cognitive resources to be able to produce these patterns of brain activity in the scanner. And for that reason, I think we are probably missing a lot of people. When we see a patient respond, we're pretty confident that it's a true response, but I think we're also a lot of patients are almost certainly slipping through the net. So For us, the future, if you like, the holy grail is to try and find a method for detecting consciousness and detecting residual cognitive function that doesn't require that the patient responds. Some method where we could simply scan the patient lying in the brain scanner and know that they were conscious. That's what we're really heading for, and I think that will be the next big thing.
Final question for you, Dr. Owen. What is it that motivates you in your work?
I find it tremendously rewarding working with patients, particularly with these sorts of patients. And it's the few moments where something really fantastic, really amazing happens that really drives my team and I on for another few years. In 2006, when we managed to show that a patient was conscious using brain imaging, I mean, that moment, it was a single moment in time, it was one patient, but I think we all really felt like we'd turned a corner and solved a really difficult scientific issue. And that was enough to really get us excited and move us along for the next few years. And the next big thing we had was to start communicating with patients. Again, it's tremendously exciting when you suddenly realize that you're able to do something that's never been done before. And that, you know, the additional reward, if you like, is that, you know, I think we're moving into a situation where we are able to do something positive for these patients, to establish whether they are comfortable or uncomfortable, in pain or not in pain, what they would like to improve their quality of life, these sorts of things. So it's both scientifically rewarding, and I think it's emotionally very rewarding too. I think that's probably what drives us all along.
Thanks very much for your time.
Thank you very much.
That's it for the show. Thanks for listening, and I hope you liked it. That was one of those conversations for me that made me want to start this whole thing called Story Untold. Just realizing the power of conversation, but also from a selfish reason thinking, man, I want to interview more people like him. If you like the show, it's on Apple Podcasts, Google Play, and Stitcher. Go ahead and subscribe. You can help me out by leaving a rating too, or pass it along to someone you think might enjoy it. Theme music for the show is by Dr. Turtle off the album You I'll Ah. I'm Martin Baumann, and this was A Story Untold. See you next time.